Hello everyone, and thank you for joining me for Handmade Hero. Welcome to the only show on Twitch where we code a complete game live from scratch. No engine, no libraries, no nothing. We do it all here. It's like one of those weird fancy restaurants where they like grow all the herbs in a garden on the roof, right? You know the kind that I'm talking about, and it's very strange. And like when you read the menu, you don't actually know what any of the things are because the descriptions don't really clarify anything. They're filled mostly with words that you've never heard of before, or that you have a vague sense of what they might be, but you really just aren't sure. And you kind of have to wait for the waiter to come over, and when they come over, you have to be like, so the salmon, and like you kind of let your voice trail off like that, and that lets them know that you really had no idea what you were looking at. That's sort of what we're doing here, you know, I'll admit that. But we do not have a garden on the roof. I've actually never been on the roof of this building. I suspect it's probably very dangerous. It's actually a rather tall building. But we do grow all of our code ourselves, and all of our pixels are hand-selected by us for the finest quality. And that is something that we're going to get back into today. We have gotten to the point where we're doing our own texture mapping. We wrote our own texture mapped renderer. And we have a bunch of things that we kind of need to look out into now in terms of picking what our next step is. So I think today is a good day for us to kind of like figure out what it is we want to accomplish with the rest of the renderer and make a plan for getting there. So if you have pre-ordered the game on handmadehero.org and you would like to follow along with the source code at home today, it is day 96, so you want to unpack day 95 source code because that is what I am working with today. And so if you want to line up with what I'm doing, that is the code to start with. All right, so, you know, we had a little bit of something that we needed to address at the end of last episode, and we kind of got to think about how we want to do that exactly. I don't remember exactly which state we left it in here, but I guess we left it in the optimized build. So as you can see, even with our completely unoptimized renderer, where we're now doing gamma correction everywhere, and we were also supporting scaling and texture mapping and rotating and all that stuff, and we got all that working, things were very slow when we compiled our build without optimizations on, but they're plenty fast with optimizations on. But as I was pointing out, it makes it a little hard to do a teaching stream if we compile with optimizations on because it makes stepping through the code be very jumpy. It's hard for me to show you things I want to show you when we do that. So what I do want to do is figure out some way that we can start to address that, and really we've got two ways that we can do that. And I feel like there's certainly some degree, there's a certain part of me that philosophically wants to say, let's not optimize the code ourselves right now, because if we start optimizing the code ourselves right now, we haven't really necessarily gotten to the point where we know everything that we want to do with it, and so the optimization may have to be changed or may be sort of rendered obsolete when later we decide we need to do other things with the renderer. But another part of me says, well, I don't know how bad that really is at the end of the day because we haven't introduced optimization really at all on this stream. We haven't talked about it at all. And so optimizing something and then having to optimize it again later is really not a big deal because maybe we kind of need to do that just to let everyone have a chance to kind of see what goes on there. So I don't really know which way I should tackle that. If I was doing the code myself, I certainly wouldn't optimize it now. But, you know, that's, you know, certain things happen differently on the stream here just because it is a teaching stream. So there's that. So what I was kind of thinking we might do in terms of moving forward on this, we've got two sort of directions we can go. One is we can add some features to the renderer right now. Meaning we can go, what are some of the other features that we might need? Can we get them in there? And can we do that with letting the code be unoptimized so we can step through it and all that? And the features that I think that we don't have in there right now that we might need, really there's two, and one of them's not so much a feature. The first one is making sure that we have a sort of a rigorous definition of what filling a pixel means and where the textures come from for those pixels, right? Because we were kind of ad hoc with it when we just were getting things working, which is a good idea because you really don't want to be too hung up on any one thing where you're just trying to get something working, so that's fine. But before we start building a bunch of stuff on top of this, it would be nice to know that we had really dotted the I's and crossed the T's in terms of where, what is our pixel fill rule, how does it operate, what is our rule for gathering texels, and all that sort of stuff. So that would be nice. The other thing that we haven't tackled, because we have tinting, and we have alpha control, and we have scaling, and we have rotation, which is most of, I think, what we probably will use for the game. But one thing that we do not have is we do not have any sort of lighting control in here, meaning that if you wanted to change the pixels of a sprite in here in some way that had to do with a directional or area-based light source, we don't really have any way of doing that effectively. So the other thing that I thought that we probably would want to investigate before we start optimizing our actual texture filling routines is to take a look and say, what can we do? We've got our little test sprite here that's rotating around, and it's nice and smooth and does all the things we wanted it to do. What can we add here that would allow us to do some more dynamic lighting on this thing, right? To sort of give it a little more of that liveliness, and so that we can allow our game to kind of be a little bit more fancy. So, I'm dithering about it, and to be honest, I don't really know which one we should do, but here's what I'm going to say. I think that if I just turn off everything else in the game and just were to render just the tree, obviously we would not have a lot of performance problems anymore, I don't think, right? Because having completely unoptimized code, if we're only running it on a very small subsection, that doesn't seem like it would be a problem. So maybe what we should do is turn all of this stuff off. Just stop rendering it entirely, which is trivial for us to do. Only render one or two things, put in our lighting, get that working, get our subpixel sort of math correct, like exactly the way we're going to do that, and then button that down, say that's the renderer, that's the features that it supports, and now let's go ahead and optimize it. It seems like a pretty sane path to me. It's very similar to the path that I would take if I was doing this for real, so that feels kind of good. And so that's sort of what I'm thinking we might do. So let's just take a look at that. Let's see what that would entail as a start to today. So if I open up the code here, right, you remember that we have our renderer kind of builds up groups of things that it's going to render, and then it issues them after the fact. So we kind of have this push buffer scheme. It builds up a list of things it wants to do, and then it renders them. Now, our test thing that we were working on with rotation and scaling that we got working was in this render entry coordinate system thing, which is really just a test thing that allows us to specify coordinates, and then it would kind of warp a rectangle so that we could learn how to do that. And that all went very well. But what we can do is recognize the fact that right now all of our fancy code is running through this path, right? And so the other code, which we modified to be gamma correct and which is kind of slow now, but that doesn't do any of the fanciness in terms of the stretching and rotating and that sort of stuff, is going through these other code paths, right? So this draw bitmap code path, for example, if I were to just get rid of it, right? So we just fully get rid of it. Oops, that's a good typo. End fee, like so. So if I just got rid of it entirely, then when we ran the program, we would end up with just the tree on our hideous pink background, right? And of course, if I left in the outlined rectangle stuff, so we're still seeing those. But we have our hideous pink background, and we have our little guy. And of course, we can make our hideous pink background not such hideous pink for the moment. Certainly, we can go in and change that. So we've got our let's see, where was that guy? There's our clear, and that's the ground chunks. So here we have our clear right here. So if we wanted to clear the screen to black or to gray or something, in fact, I guess maybe I'll pick a gray here, like so. If we wanted to clear to a gray, we could do that, and then we have a pretty open ability here to kind of play with this. And if I go ahead and take out the optimization request to the compiler, so we go from having that OD to that O2 to having that OD. Here is the slow version running. And that, again, is totally fine speed-wise, I think, right? So I feel like for the most part, right, this is probably good for us. And we can just work on this for a couple days, get in the new features that we want, and then switch over to optimization at a time when it's probably a little bit better. So unless anyone has some huge reservations about that, I think that's what we're going to do. So, all right, let's start with, first of all, we don't really need this guy to be rotating anymore for the moment. We can stop with all of the rotation. So I'm going to go ahead in here and just have that rotation stop entirely. So there we go. And now our tree is there, just kind of sitting upright. So what I want to do is kind of introduce what the concepts of lighting here are. We won't go too into detail about some things, but then we'll kind of start to try and figure out what it is that we want to implement in terms of lighting. Okay. Here we go. Where's the blackboard? There's the blackboard. Okay. So here we are on day 96. And we want to talk about lighting because lighting, in fact, I'll quote Doug Church here, one of the primary, you might even say the primary person who made Ultima Underworld. Lighting is the sound of graphics. And that is Doug Church. Now, Doug Church is very smart and you should listen to him, but I can understand why taken out of context this quote might seem a little strange. What he was trying to say at the time, and it is now an absolutely classic quote in my opinion, what he was saying at the time, it was actually John Carmack had given a private demo of Quake before anyone had seen it in the public. And one of the big things that he had added since the last time the people in this sort of private demo had seen it was he had added the shadow maps, right? And the shadow maps really dramatically change the look of a game because when you look at something with no lighting, it just kind of looks like this flat, arrangement of colors on the screen. It just doesn't have any sense of place or any sense of depth to it. And when you put in that sort of realistic shadowing, or even not that realistic shadowing at some level, just some degree of allowing your eye to kind of see that sort of way in which the light plays off the space, it really, changes dramatically how present that space is and how much that space feels alive and feels real, and it gives it a lot of dimensionality there. It gives it a lot of depth, right? And so what he was saying with this quote was he was referring to the kind of well-known sort of similar sort of thing to this, which is that if you play a game without sound, you'll be shocking at how much worse it feels. Even though you're not really consciously aware of it, the sound adds so much to the look that, you feel like a game just doesn't look as good, right? If there's no sound with it or if the sound isn't good. And if the sound is great, it makes the game look better in this weird way because all of the actions are accentuated with these sound effects and it really sort of brings it to life. And so what he was saying with lighting is the sound of graphics, he was sort of likening lighting to sound in that way, which is that like you can do all this great modeling and you can have these great art assets, but if you don't light them well, you lose this very important accentuation that really makes things come alive. And so it's true, in a 2D game, it's not as big of a deal in a 3D as it is in a 3D game because the artists do a lot of baking of the lighting into the sprites that they do. But we still would like to have dynamic lighting in the game because there's a lot of accentuation that dynamic lighting can do. Just to give some simple examples of why we might care about dynamic lighting, we might, for example, want to have, given our tree example, if we've got a bunch of trees in the world and they're around, a little campfire kind of thing that's happening here, right? We might want to have that campfire flicker against the trees. That's just it sets that scene really nicely, that sort of thing. Similarly, if someone is if some kind of wizard here, with a long kind of beard or something like this, and who's very angry because of some reason that like J.R.R. Tolkien took 5,000 pages to explain, and that maybe still doesn't make a whole lot of sense, but you can ask some pedants about it and they'll explain to you all the backstory. He casts some fireball, right? And so here's the fireball that's there, and it's going forwards. And as that fireball moves by the trees, for example, right, you want to kind of see that light play off them in an animated way, first lighting up here and here and then here and here, right? You want to see that. And that really accentuates the motion in the thing, and again, it makes it feel like they're all in the same space together. You can also have the absence of light tell a story in a similar way. If you have, the shadow of something that's very large come over a space, that's all that sort of stuff is examples of how in 2D games you still do want to have some control of lighting if you can't help it, right? So what are the ways that we can get lighting into our game? Let's talk about lighting in a sort of abstract sense, and sort of then we'll talk about how we can actually get our sprites to have some of that, because again, we don't have fully 3D representations here coming in, so we don't have the complete information we would need to do full lighting. Okay, so lighting is fundamentally a directional effect, right? And what I mean by that is light is traveling in lines. This is true in the real world for the most part, right? When you think about light in the real world, we're talking about photons that travel in straight lines. I mean, modulo relativistic effects and all these other sorts of things, but traveling in straight lines between 2 points, bouncing off and traveling in another straight line. Eventually, these photons, they all start at some light source, right? You know what I'm saying? They all start at some light source. And they bounce off a bunch of surfaces in the world, and they fundamentally eventually come back to your eyeball, right? That's your eyeball, where you collect those photons. And in the process of collecting those photons, your eye constructs an image. And what that means is all of the effects that have to do with lighting are very much about the direction in which the light was coming from at any given time. And what this unfortunately kind of means when you extrapolate it out far enough is that doing lighting correctly is actually extremely difficult. And I'll try to give you a little bit of a picture of why real lighting, if you were to do it completely correctly, is extraordinarily difficult. So if you were to compute the lighting, what actually happens with lighting, and let's take out everything from this equation except the bare necessities, okay? So all we're going to have is we're just going to have the sun. Here is the sun, right? This is the sun. We are going to have one surface. That's it, right? So the light comes down, it hits this surface, right? And we're going to have just your eye, just your eyeball. There it is, right? So the light comes down, it hits it, it comes back in here, and it hits your retina back here and produces an image for your brain, right? So let's suppose that that's what we've got. So even in just this situation where this is the only thing that's happening, computing the lighting for this effect, no matter what this surface is still incredibly difficult. There are a few surfaces that can make it easier, but for the most part it's incredibly difficult. Because the way that light bounces off a surface is highly chaotic. Most surfaces that you see in the real world actually scatter light in many directions when it hits. So when the sun hits this surface, right, it bounces in all directions typically, right? So photons come in, billions of photons come in from the sun. They strike this surface and they bounce off in all directions. Some of them bounce off in the direction of your eye, and those are the ones you see. Others don't. Others bounce off in other directions, and there they go, right? Now, when it bounces off a surface, right, the photons, they actually have a wavelength, okay? And so for those of you who don't know anything about light, light has wavelengths, right? And wavelengths are essentially, I am not a physicist, so I'm not even going to say what wavelengths are. I'll say what I think of wavelengths are, but I'm sure a physicist would correct whatever I'm about to say. But point being, light, the photons that come in, there's this whole notion in physics of particle-wave duality and all this stuff that I don't even pretend to understand. But basically what happens is you can think of the light as oscillating, like a sine wave kind of a thing. It's oscillating. So when it's coming down this line, it's actually oscillating. And the speed at which it oscillates is actually, it changes, right? In other words, the wavelength, the distance between when it crosses the same point, it changes depending on the light source. So when the light is emitted, it has a certain wavelength, and those wavelengths are the colors that we perceive. There's infrared, which is colors we can't perceive down in the heat spectrum. Then it crosses into red, right? Goes through all of the colors in the spectrum until it gets to violet, and then ultraviolet, right? Which we can't perceive. So there's more wavelengths in both directions, but we can't see them. We might be able to feel them, or we might be able to see them once they hit something and change back into visible light, but for the most part, we can't see anything on either of those two sides, okay? But everywhere else in here, we actually see this light. And the way that we see this light, and incidentally, this is why monitors, if you ever wonder, why are monitors RGB? What's the deal with that, right? Because honestly, RGB isn't a thing in the real world. It's not a thing, right? We actually have continuous wavelengths of light that can represent any color. It's not a question of there being red light, green light, and blue light. That's not a thing, right? There's actually all of the colors are real and have their own unique wavelength, right? Well, the reason RGB is the thing that we use is because our eye actually only has receptors at those points, right? So basically, in your retina, okay, in your retina, you have sensors for red, you have sensors for green, and you have sensors for blue, okay? And the way these sensors collect light is they collect it in sort of an overlapped fashion, right? Like this. And so your green receptors don't only catch one specific wavelength of light, they respond more strongly or more negatively, more strongly or less strongly, depending on how far the wavelength from light is that hits them is from green. So by looking at the combined activity of your red, green, and blue sensors, what your brain is effectively doing is trying to figure out where the light wavelengths were, that actually hit. So like something comes in here, right? And it's cyan or something, right? And it sort of is or I don't know what color it is. I drew that line in a place that I'm not sure exactly what it is. But it's registering on both the green and the blue, let's say, right? And so it's there and there, it's registering. You'll perceive that as a color that's a mix of green and blue, one of those colors that's in here, right? And if you happen to have light that's coming in at multiple wavelengths, right? You can have light coming in that's got photons of all sorts of different wavelengths. That's maybe a light source is emitting lots of different kinds of photons, something like this. You can have things like white, where there's some coming in here and some coming in here and some coming in here and whatever, and it's affecting all of these sensors evenly, et cetera, right? So RGB tends to be a very effective way to represent colors because that is basically just us saying, all right, let's just output light at the three things you can perceive, and we'll just fool your eye into thinking it's seeing something like yellow, for example, by highly triggering the red and the green light with red, by putting out red and green light that triggers those two sensors, and not putting out any blue. So your eye goes, oh, that must be some yellow light coming in. But surprise, it wasn't yellow light, it was red and green light. In the real world, there may be such a thing as yellow light. You may actually be seeing yellow when you see yellow, not a combination of red and green. But you'll never know because you can't see it. Now, there are other animals that have more sensors in here, and in their world, they can tell the difference. So if they were to look at a monitor, they would be like, your monitor is awful. That doesn't look anything like the world looks. You guys don't know anything about technology. That's what they'd say. And we would look at the picture and go, what are you talking about? It looks exactly right. It's just like you went out and took a photograph, right? So don't talk to those animals, okay? If there's any lesson that you take away from today, it's don't talk to animals with more color receptors or more color wavelength sensors than you. Okay? Because frankly, it's just not worth the hassle. So I think that's the main takeaway. But let's press on and continue. We've got about, how much have we got? We've got 35 minutes. So I'm going to press on and try to get to the actual lighting, even though this is really the main takeaway. Okay. So back to our picture. So we have wavelengths of light. Wavelengths of light are coming in. They're hitting the surface, and they're scattering in all directions, some of which come to your eye. Now, the problem, and the reason that I said it's such a fantastically difficult problem, is because this is true for any incoming direction. Okay? So if there was light coming, if you had a second sun, for example, and there was light coming from there, maybe it's the dark crystal. If you had a second sun that was coming here, it would also scatter light towards your eye. Okay? So what you see when you look at a surface is you actually see the aggregate effect of all of the light sources scattering light towards your eye. And the reason that this is a problem, even if you only have one sun, is because everything else in the world is also reflecting all of those photons. A lot of them are bouncing right back to that point that you saw and then scattering to your eye. So in order to compute even the lighting, the correct lighting at just one point in the world effectively requires computing what the incoming light was for all of the directions emanating from that point. It is an incredibly, incredibly difficult problem. It is why accurate lighting is probably the hardest thing to do in computer graphics. Now, if that wasn't bad enough, it actually gets even worse. For reals, the light doesn't actually just bounce off the surface. The light actually travels into the surface, then back out. Okay? If we were to talk about a real surface, it actually has some thickness to it. And let's say it could be something very complicated, like wax. And what happens is when photons hit the surface, anywhere, not just the point you're measuring, but anywhere, the light goes into the surface, and the photons actually pass through. They maybe don't hit anything. But then they do hit something inside the surface, right? They bounce again, then they hit the exit point and happen to scatter back to your eye, right? This is called subsurface scattering. So technically, if you really wanted to do lighting correctly, not only do you have to know all of the light in all of the world that could possibly come back to you, right? You need to know all of this, but you also need to know all of the light that could have come at you from inside the object that you're talking about. Now, fortunately, a lot of objects are so opaque that you just don't have to care. But if you really wanted to do it right, and you want to support wax, and you want to support waters, and you want to support Dr. Pepper under a flashlight, you got to handle all of this, right? Now, what makes surfaces look different? It's a good question, right? Because you look around the world and all the surfaces, they look different. They have different colors, okay? They have different shininess we talk about. Some are translucent, transparent. We've got all these sorts of things. What makes surfaces look different, right? And the answer is what they do to the photons during this process, okay? So there are a couple primary aspects that you want to think about when you're thinking about lighting. The first one is for any incoming direction, okay? And we can start to talk about these directions very specifically. I'll do the 2D version here and I'll draw the 3D version in a second. But for any incoming direction and any outgoing direction, right? And so maybe I'll draw that a little bit differently. Let me draw them this way so that they're both kind of on the same angle system. Do that way, right? So here is one angle and here is another. We'll call that phi, we'll call that theta. So for any two angles, and one I have, we'll call this the angle of incidence. So this is the way the light is coming into the surface, right? So here's the light source. and then the angle that we're viewing, right? So here is our viewing angle, the thing that we're actually trying to measure along. So there's our eye. For any two angles, every given surface in the world will have a different amount of light that they tend to reflect back, right? And so if light is coming in at this angle, theta, right? If it comes in at theta, right? We know that it goes out at phi for some percentage, okay? Some percentage of the photons will go out. And for every surface in the world, that percentage will be different. And that is what controls the shape of this lighting. If you imagine now, we need to define it for every one of these and every one of these combined. So it's effectively a function of both theta and phi, right? It's a two-dimensional function saying for every angle that I view and for all of those angles, every angle of incidence, there is a different percentage of light that I'm going to reflect in that direction, okay? And obviously this percentage should all sum up to the total amount of light, so they should all sum up to 100%. So all of the light that comes in, should go out. Well, I shouldn't say that. Should sum up to that or less, because it's going to absorb some amount of light as well, right? So it's not going to sum up to 100%. It's going to be less than that. It can't emit more light than it takes in unless it's photoactive in some way, which I suppose you could also simulate, right? So this is what controls the look of that surface, and if we extend it to the full range so that you can actually talk about in here as well, then you're talking about handling what it looks like interior, but you need a few more things such as how stuff scatters internally. So you need a few more parameters to talk about how light bounces around in here as well. But this, measured along, say, R, G, and B, is what defines all the surfaces, although if you really, again, wanted to be absolutely precise about it, you would actually have to say, well, also the wavelength. Because technically, different surfaces can handle different wavelengths differently. They don't have to obey our breakdown into RGB that we use as an approximation, right? So, people will often use things like spectral calculus and stuff like this, if they're really trying to do accurate rendering, to handle things where different wavelengths of light behave differently when they hit, right? So this is an incredibly difficult problem. And again, I just wanted to kind of impress upon you how difficult lighting is if you wanted to do it correctly. And to set the stage for saying, we will not attempt anything like this because, first of all, you don't usually do anything like this in real time. You often are going to use some approximation. But we will be using much more simplified models of how the lighting works in order to be able to achieve results in real time. Okay. So, what sorts of surfaces do we tend to actually want, right? Because that was all of them. Let's talk about ones that we want. So typically what we want to have in the ability to simulate most of the time, right? If we're just talking about simple artistic concerns here. What we typically want to have is diffuse surfaces, I guess I would say glossy surfaces, and reflecting surfaces, And these are just my terms here. I'm not trying to introduce any standard nomenclature. I'm just saying these are some ways you might think about them. And what those are is a diffuse surface is something like chalk, right? It's something that really doesn't have a bright highlight on it, okay? When light comes in, it scatters in all directions evenly. It's not biased. So no matter where the reflection comes in, it's going to scatter in all directions evenly. It just distributes it diffusely, right? Glossy surfaces, well, let me do reflective surfaces first. So highly reflective, I'll call these highly reflective surfaces, are like mirrors, right? These are like mirror surfaces. And what they do is when the light comes in, they reflect it directly back out again. It doesn't scatter. Nothing goes in this direction, nothing goes that way, it goes right out the opposite direction, right? And that produces a mirror. If you think about why that is, it's actually kind of obvious. All of the time that you look at it, it just basically is as if there was your eye sitting there looking back in the other direction, right? It's very straightforward how that happens, right? So that's ends up being sort of a mirror surface. And a glossy surface is somewhere in between. It's one where light comes in and most of it, right? A high amount of it goes out this way, but a little bit goes out in the other directions, right? And typically, so there's sort of a lobe here, you might say, right? So the reflectance, is kind of less over here, but then it kind of gets bigger in this direction and kind of goes like that, right? So these are the kinds of surfaces that we tend to care about because they are the ones that we could use artistically to get a reasonable set of, approximated effects in our games that allow the surfaces to look a little more realistic. Okay. So, given this, what we typically end up with, right, is we end up with approximations for those things. That was the worst, I'm going to write that again. That was the worst. There we go. That was some awful handwriting. So what we tend to do is we try to come up with approximations that will let us do reasonable jobs of these things, okay? And originally, back in the old days, when lighting was really, really bad because computers were too slow to do anything good, typically what you had is you had literally computations that look almost exactly like the diagrams that I was drawing. Only they didn't even really have much of this stuff. They were like, basically, I have a point that is sending light at my surface, right? And then I have a bounce out to the thing. And all I'm going to do is have some fall off that determines, how sharp the lobe is here. That's all I'm going to do. So light always comes in from just one place, right? The source of light is one point. And what that ends up looking like is it looks like somebody shining a flashlight, basically, on surfaces, right? And yes, you can, by controlling, by looking at this angle, the difference between the incoming and the outgoing, right? I can make the surfaces look more or less shiny by sort of controlling whether or not the light that gets bounced back falls off sharply as you move away from that primary reflection angle, right? So if the primary reflection is here and, we're viewing it up here, if it's getting darker due to that, then, the surface will kind of have a nice shininess. As I move here, it gets brighter and so on. And you can think about this surface, right? Like let's say that I was looking at a sphere, right? We're evaluating this whole thing at every point on the sphere. So basically, if you want sort of a nice bright highlight there, and then, it's dark everywhere else, we can do that sort of thing. That's not that big of a deal, right? But it always looks like just one light shining on a thing, and it's usually very harsh, right? It usually has a fairly harsh shadow because there's no light coming from anywhere else. It's black on the back here unless you add in some fake light and all that sort of stuff, right? So old approximations tended to be that way, and they were pretty harsh. Now we could, of course, live with stuff like that in what we're doing because we already have art that's drawn that imagines that there's all of this light coming in, right? And so if we were to just overlay some lighting like this on top of it, that would probably be okay, right? It would basically just add in highlighting here, and we let the fact that the artist drew it with some ambient lighting take care of the rest of it, right? So, this would probably work for us, right? Because we're not in 3D and we're not having to recreate the entire scene with all of its lighting ourselves, we do have some leeway of picking old school, fairly broken and lousy approximations to lighting because what we need the lighting to do is very limited. We don't need it to recreate the entire look of the lighting. The artists already did a lot of that, right? But we may be able to do something better and we'll play around with it because modern approximations will often do things that involve, say, light probing, right? So light probes are ways of trying to get around this problem of only having the computational power to deal with single points that say where the light is coming from. Because remember what I was saying back here when I first introduced this, the light comes from everywhere, right? The light comes in from everywhere. And so when you compute things as if there's just 1 or 2 point light sources, it's never going to look like the real world because you're never in a situation where light is only coming from 2 light sources. Because even in a room that only has 1 physical light, and even if that light was almost a single point, like it was a really tiny point light, the light bounces all over. And once it's bouncing, it's coming in from everywhere. So every surface is still getting light from everywhere, even if there's only one actual thing that we would call light. And so what we've done nowadays in games to try and get around that in a lot of cases is we try to come up with some way of allowing approximations to all of that incoming light. Now that would be incredibly difficult for us to do if we were trying to solve it directly. You end up with doing things like that ray tracers do, where you kind of try to do this stochastic sampling and reconstruct the light field. There actually are some things you can go look at. There's a thing called Brigade. It's a real-time ray tracing renderer that they've gotten fairly far on. It's not the kind of thing you could really use in a real game yet, but it's getting better. So there are times when people just full-on say, all right, let's try to simulate the whole thing. And maybe someday when computing power gets that advanced, you'll actually be able to use that in a game, but not today. We're still a ways off. If it ever does come to pass, it's going to still be a few years away. But what we can do is use things called light probes. And what light probes are, or you could even I'd say this more sort of generally say indirect light sampling. And basically what we're doing here, what we're talking about, is can we build some systems which compute effectively like lookups tables or things that we can go quickly access that would give us a fast way to compute all of the contributions of the light that is coming into a surface, right? And so oftentimes what you'll see people do is, for example, let's suppose that I want to light again, I've got that sphere, right? And I want to light this sphere, so I want to compute the lighting at all of these pixels on the sphere and so on and so forth, right? Well, what people will often do, for example, is they might render a cube map, which is essentially as if you were to start at the center of the sphere and render out in in 6 directions, right? 6 orthogonal directions from the sphere. Render out images that you can imagine if you were, inside a cube, like so. If you're here, what you'll do is you'll render out and actually render what the world looks like on all of the faces of the cube, right? Does that make sense? So essentially, you made a box that is what the sphere kind of sees when it looks out from its current direction, right? Well, what that effectively is it's like a condensed lookup table of all of the light, right? It's like a condensed way of saying what all the light looked like coming into the sphere. And you're like, well, that's great, Casey, but who cares? Because now I still don't know how to compute any of this stuff, because I would still have to go look at all of the pixels on these cube maps. Well, yes and no. What you then do is you might take this and you might start downsampling it. So let's say you rendered these at 256 by 256 by 256, right? Well, it's really just 256 by 256 and 6 times, right? So it's 256 by 256 by 6, one for each face, right? Suppose I then blur these down to 128 by 128 by 6, right? And all the way down to 1 by 1 by 6. Now I would have a bunch of cubes that are blurrier and blurrier versions of the light that's coming from around the room. What good does that do me? Well, it means I can now simulate the effect of all the incoming light, right? Like in this diagram, by saying, well, okay, if I know that my surface is like that chalky surface and all the light bounces evenly, then I'll just look at that most blurry cube, because that's what it's going to look like. Whatever the average light that comes in, that's a pretty reasonable approximation, right? If instead I've got the other kind of surface, I should be using my other diagram for this. So if I've got that, I can just look at the blurry versions of the cube, and that tells me roughly what the aggregate light that comes in looks like. If instead I've got points that have sort of a more pronounced reflection lobe there, what I can do is sample this direction out of one of the higher detail cubes and add it to a weighted version of the lower detail cube sample, producing a nice averaged glossiness between the two, right? So you get some reflection, you get some incoming ambient, right? And furthermore, if I'm just doing highly reflective, I just sample the highest resolution cube always and don't add in any of it, right? So there's ways that you can start to approximate these things, right? And that's in 3D. So what do we do in 2D, right? What are we going to do? So we have two real problems in 2D, right? Problem one, we don't know what the surfaces are. In 3D, you always know what your surfaces are because they're polygonalized. So you know what they're shaped like, you know what direction they're facing, you know everything that you need to know, okay? But we have no idea in 2D rendering what our surfaces even are. If we look at this tree, all we've got is colors, right? And the reason that you and I see this as an actual 3D shape that we recognize as a cartoony little cute version of a tree is because our brain is interpreting those colors and the value change, sort of the brightness change of the greens to imply that there is sort of a tree shape there, right? So we could go in as humans and kind of roughly know where each of these, what, kind of made up these surfaces, but that's incredibly difficult for a computer to figure out because it doesn't even know this is supposed to be a tree. Those are like machine learning problems that are incredibly difficult. And so the first question is, what can we do to even know what direction or facing any of these surfaces are? Because remember, all of this stuff was based on reflection, right? It was based on knowing the direction the surface was pointing. If the surface was pointing that way, it's going to reflect things a lot different than if it's pointing this way. Just like you throw a ball against a wall, it matters which way the wall's facing, depending on, how the ball's going to bounce, right? And so all of those reflectance functions are in terms of the direction the surface is pointing. We don't know what direction these surfaces are pointing. We have no idea, right? So that's our first problem. And one solution to this is to have normal maps for your sprites, right? And what a normal map is that saying, okay, I've got a color map for the sprite that says what the colors are. And then what I do is I augment that with a bitmap that basically has at each location, instead of storing RGB, what it stores is XYZ of a vector that points in the direction that the surface is pointing at that time, right? So it's like a bunch of little tiny vectors that just say, for every pixel, what direction that pixel surface was pointing. Now, typically, you don't actually need to store the XYZ because it's a normal, so it has a length of 1. So really, you only need to store the X and the Y, or the Y and the Z, or whatever, depending on what coordinate system you want to use. You only need to store 2 of these, and you can reconstruct the other one. But that's a totally separate topic, right? Point being, you store vectors in here. So that works quite well for solving this problem. The problem with that, where do you get them? The artist painted the bitmap. They can't paint a normal map. You can ask them to paint like a bump map and generate a normal map from it, but then it takes your artist a lot more time, blah, 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 blah. There are programs that try to generate normal maps for you. Who knows if they'll work particularly well? I could certainly try passing ours through there. We don't know, right? So this is kind of a problem for us, but it's an art asset problem, not a computational problem, because we can implement this and we should. So we'll go ahead and implement normal maps and then hope that we'll have a way to produce some relatively useful normal maps from our stuff. If we don't, then what can we do? At least we tried, right? So we'll implement that as a solution for the 2D problem of not knowing where the surfaces are. And then if we can't get our assets to have reasonable normal maps, maybe we'll do something that fakes them in a really bad way and just leave it that way. I don't know. But point being, we'll have the computational stuff in there to handle them. So that's problem 1. We also have problem 2. Problem 2 is we don't know what the light field is. In 3D, we have the luxury of being able to do this because the whole idea behind 3D games is that they're rendered in 3D, which means you can set the viewpoint anywhere you want and render in any direction you want. So if you want to know what the light field is at any particular location or family of locations, you can usually come up with a way of placing the camera and rendering so that you can see what it looks like there, and then you can use that for sampling. But we can't do that. So we have no way of placing a camera in the scene and rendering things in various directions to see what the lighting is. So we needed to come up with something that will allow us to produce a light field we can sample. Now, one way we can do this is just by using point lights, right? This was the old scheme that I was talking about before, where we just full on just say that there's light coming from a point somewhere, and then that's just used in computations, right? We can do that. Okay. And, you know, if worst comes to worst, this is all we will do. We'll just put in point lights and we'll let the point lights shine onto the surfaces, right? But we may be able to do something better by like doing some kind of light rendering, right? So what you could imagine us doing is you could imagine us making a thing that sits over the screen, a bitmap that we're going to render before we render, a pre-render pass, right? And maybe that pre-render pass, you know, it's not 1920 by 1080, maybe it's 192, you know, maybe it's subsampled by 10x. So instead of 1920 by 1080, right? No, it's not going to be that. It'll be like 192, you know, by 108 or something, or maybe the closest power of 2 to that. So maybe it'll be 128, you know, 256 by 128 or something like that. So we've got basically a mat, not a mat. That's a real thing. So a sort of a separate frame buffer, if you will, a light buffer that sits on top when we start, and we render our lights. We figure out a way to render lights in here in some kind of useful way, right? So for example, what we could do is we start by rendering into this thing, you know, anywhere that we want lights, we render little splats, right? So like here are the actual lights that we have in the world or something, right? And then maybe we like diffuse those splats programmatically. So like we, you know, let those blur out. We like do some kind of blurring on them, right? And then we take wherever there are entities and we subtract light from there to darken it or something, right? I'm totally making this up, but you see where I'm going with this, right? Some kind of buffer that we can draw stuff into that we can then use when we are drawing something to sample as if we were looking out in the various directions, so that when we grab a normal and we want to know what the light is, we can go, oh, okay, yeah, there's some light coming from over there, and we're going to put it in to our lighting equation, right? So, like I said, don't know, and we could do this, you know, and so basically what this is doing is it's making little light probes, like maybe every like 8 by 8 of this is kind of considered a little light probe, you know, so when you're sampling, you're just sampling the 8 by 8 near you, you know, whatever. You see where I'm going with this, right? And again, light is a directional problem, so it's pretty tricky because technically, like if we have a reflection or a mirror over here and a light source all the way over here, you should be able to see this in that. And how do we do that kind of a search, right? It's pretty tricky. So again, don't really know what we're going to do here. I haven't thought about it at all. And I've never tried to do anything similar to this since I normally work on 3D stuff. I don't do a lot of 2D work. But point being, we'll try. We'll give it an honest go of trying to sit down and think through what are some ways we could accelerate the lighting lookups. What are some things we could do maybe that would lead to some more interesting lighting that had more dynamism and made the scene feel more cohesive, right? So I think I'll probably wrap that up. I think we've covered most of the lighting stuff. We haven't talked specifically about how to compute lighting, but that's okay. I just wanted to give you the overview today. And so probably what we'll do now is, you know, maybe tomorrow, let's implement this. Because it's actually pretty straightforward. So we'll talk about the actual equation for lighting for one bounce, and we'll do our normal maps. And then we'll move on to seeing what we can do here. Because, like I said, don't know what we'll be able to do, but we'll give it a shot. All right, so with that, I will go ahead and push us over to the Q and the A. If you have any questions about lighting, please put Q colon in front of them, and we will tackle them, or try to anyway. Questions? Who has questions? Questions, questions, questions. I guess we don't have any questions. Everyone was like, yep, lighting, awesome. I totally understand all of it now. So is this why animation studios like Pixar have supercomputers for the rendering? Yeah. So basically, like, you know, the weird thing about lighting is we've actually understood for a fairly long time, I guess you might say, how to do pretty good computations to compute what the lighting is. It's just they're so expensive to do because they're four-dimensional or worse problems, sampling problems, that we just don't have the computing resources to solve them. So yeah, if you want to produce high-quality images, one solution you've always had is you can get significantly better by throwing more electricity at it. And so yeah, they can produce much more higher quality lighting. The other reason that they have supercomputers is because they spam a lot of geometry at stuff, like for fur rendering and stuff. They'll often do that, and so that eats up a bunch too. But it's usually lighting. Lighting's usually what does it. It's very hard to actually have geometry cause you to need a supercomputer, but lighting is rough. What about shadows? So the interesting thing about shadows is shadows isn't really a thing. Shadows is just when you don't get light. And so really these techniques handle shadows, right? As well, when you think about it. But because they are so approximated, sometimes if you have situations like where you want sharp shadows, because this will actually give you, when you're doing stuff like this, it'll give you sort of very diffuse darkening. But if you want sharp shadows like the sun on a lamppost and you get that long thing, right? Then typically what people will do for that is what's called shadow mapping, right? And what that is they will actually do the computation for a light directly for its immediate contribution. So just its direct lighting, right? As opposed, so none of the bounce lighting, that's all done, using the light probe kind of thing. But what they'll do is they'll take the direct lighting and they'll actually render a view from the source light, right? They'll render a view directly from the source light, and they'll use that view to let them know what the source light saw and what it didn't, and that will produce the shadow. Because when they light things, they look up into the light and say, did the light see me? No, it didn't. Okay, I'm in shadow. So that's shadow maps. And I don't think we'll need to do those because really, we don't really need to. I don't think there's anything in our game where we're going to really want to get super crisp shadows. And if we did, we could just probably fake them with sprites. So I feel like what we need dynamic lighting to do for us is not really shadows. That doesn't really define the look of a 2D game in this style very much. What we want is more that environment lighting play, that sort of, if there's green poison somewhere, I want to see some green light bounce off of stuff, and I want to see things that, are shadowed from the green light not have it on there, but that's the extent that we want shadowing. And so I feel like a light propagation scheme is going to be more what we want, and shadow maps would probably just be a waste of compute for us, I think. But it's always hard to say. I was looking for a build design doc to follow if you have one. I'm not sure what a build design doc is. If you let me know what a build design doc is, I can tell you why we don't have one, because I'm almost certain that we don't, but I don't actually know what it is. Do we also plan on having a day-night cycle and dynamic shadows where they stretch and fade depending on the position of the sun? No. Well, okay, so although I can appreciate why it might be nice to look at that from a technical standpoint, well, I can say two things. I appreciate why it might be nice from a technical standpoint. Unfortunately, I don't like daytime for this game. So this game takes place entirely at night. So we will not have a day-night cycle in the game because it's supposed to be kind of an adventure in a forest at night. So it never turns to be day. But that said, the way that we're doing shadows by having them in a separate pass would allow you to do that actually pretty easily. So I think our tech would just support you just fine for that. And so maybe if someone wants to make their own version eventually that does a day-night cycle, hopefully they wouldn't have too much to do. Question, light feathering, example in a window or tree. Light feathering. Are you referring to translucency? If you could be more specific about what you're asking, I'm not totally sure. Sort of on topic, would you consider doing a true 3D lighting or ray tracing discussion lesson at some time? I mean, I wouldn't say necessarily no, but it's, you know, that would have to be way after Handmade Hero, because it's just not something that applies to this project, you know? How do you account for infinite reflections if there is a mirror that reflects light into a mirror that reflects light back at the first mirror? Well, so there's two sides to that question. The first question is, how would you handle that if you wanted to do it in a synthetic environment? And the answer there, I suppose, is it depends. You're going to have to do some kind of hack that, you know, eventually terminates the thing after a certain number of bounces or something like this. But if the question is, what do you do about it in the real world? The answer is the real world has no such thing. Every time a photon bounces off a surface, it has some percentage chance of being absorbed or scattered in a different direction by that surface. And so eventually there is no such thing as a mirror that can bounce light back and forth infinitely. Eventually the light will get absorbed. And that is why if you look at mirrors that face each other like that, the reflections actually get darker eventually, because it can't keep sending the light back and forth ad infinitum, because I don't think there's such a thing as a pure, like a totally pure reflector. I could be wrong about that, but I'm pretty much positive no one's ever invented any such thing. Also, obviously you have dust in the air, so you have to also be in a vacuum, because light, when it hits the air, there's things called volumetric scattering, which we didn't really talk about, which is basically just the case where, so if you remember, I drew this thing where I was saying, well, technically you have to worry about what's happening inside the surface. Like I used wax as the example. And really, the whole world works that way unless you're out in space. So if you're in our atmosphere, then actually anywhere in here, the light could also decide to take a detour, because it could hit some particle in the air and bounce. And that's why you have things like, you know, Rayleigh scattering and mist and, you know, the fact that things that are further away appear to be more washed out. That's all because there's actually scattering going on in the air as well. And so with your two mirror example, you'd be hitting that as well. Every time the light transit between the two mirrors, you would end up losing some of it to scattering that was happening just due to air molecules. And so in the real world, there's no such thing as light that bounces back and forth infinitely, as far as I know. Could you repeat that? Bunny Mancer, I don't know what you want me to repeat. Abner Coimbray, heated debates of why we need to go through the trouble you're going through. Just use Unity, Kappa, many newcomers. So yeah, I mean, I've said it a million times, but obviously for newcomers, they haven't ever heard it. So this is not a programming stream. You know, this is not game development for dummies. I won't even write that on our Blackboard. But you know, this is not how do I get a game up and running as quick as possible. Because there's tons of that, right? If all you want to know how to do is boot up Unity and whatever Unity can do, that's your game, right? If that's what you want to do, you really don't need to stream, obviously, because you know, you can go just watch some tutorials. In fact, I think Unity's site probably has pretty good tutorials on it. I've never really watched them, but I suspect that they've got good training materials. I mean, why wouldn't they? That's the whole point. They want people to use the engine. Same thing with Unreal or any of these other things, right? Game Maker. So if all you want to do is just get a game up and running and you don't really care about pushing any boundaries, or you don't really care about being able to zero in on quality and that sort of stuff, then yeah. But this stream is different. This stream is about learning how those things work, right? It's about being able to extend your ability past what the engine is capable of doing out of the box, right? And there's two ways that this can affect you. One, it can allow you to do things that other people can't do, because once you know how the lighting works, you are much more empowered to be able to replace it, modify it, hack it, do whatever you need to do to get the effects that you want, right? And that goes not just for lighting, but everything that we talk about on the stream. But also it means you're on the road, if you want to be, to sort of actually being able to work on that higher level yourself, right? You could start making your own engines. You could start making your own Unity plugins. You can start essentially giving yourself much, much more power, right? And, you know, it's kind of like saying, why would I want to learn how to, you know, build a car when I can buy, you know, I can go buy a Honda Civic, right? And it's like, well, yeah, I mean, if all you want to do is just drive a car around, you should just go buy a Honda Civic. But if you're someone who's interested in the future of cars and about building the next car that does awesome performance stuff that no one else does, or you wanted to invent the electric car because you were Tesla, you were Elon Musk or something, right? That's what we're talking about in this stream. So this stream is supposed to be the place that you come where you can start getting into, at a sort of starting at the ground level, getting into that real deep game development where you actually learn how to do everything, not just, hey, well, if there's a button for it in Unity, then I guess I can do it, but if there isn't, I can't. Is 2D worth going for when it becomes more complex than 3D? Well, so, you know, I can appreciate why sometimes on the stream it may look like 2D is more complicated than 3D, because anytime I'm going to mention 3D is that circumstance, right? And so every time I'm going to mention 3D, it's going to be because I'm saying, well, in 2D we don't have access to this, so this is why we're, you know, why it's a little harder for us here, right? What you don't see is the 8 billion things that are harder if you're implementing stuff in 3D, because we don't have to do them, right? So 3D carries with it just huge amounts of hard stuff that you're just not seeing because I'm not having to teach you how to do it because we're in 2D. And it's a really good idea to start with 2D first, because that is the case, and usually, you know, I mean, I'll give you a very simple example, right? Let's suppose we wanted to do this, okay? All of this stuff that I'm talking about here, you actually have to implement this stuff in 3D. It's incredibly complicated. You need to come up with surface reflectance functions. You need to come up with approximations to those surface reflectance functions. You have to source them from somewhere. How are you going to do that, right? You have to handle transparency in orders that you can't predict. So you have to sort the stuff in your scene into 2 groups, and then sort the transparent groups so that you know that you can handle them in the correct order, right? You then have to worry about, when you're doing sort of this rendering here, right, this cube map rendering, how often and where are the cube maps going to be placed, and what are the numerical consequences of where the cube map was relative to where the object was, because they're not going to be exactly right. So then you have to interpolate from multiple probes in the world, like to try and triangulate your position. And then wait a minute, some things in the world, if they're translucent, they should allow light to pass through, but they'd have to color that light and blah, 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 right? So there's like, it's incredibly complicated if you actually want to do it in 3D as well. So I don't mean to give the impression that 3D is easier or anything like this. And also, you know, you can see this in a lot of systems, like even when you use a licensed engine, they're only now getting to the point where you don't have to do a ton of pre-computation. Like Unreal 4, I think, finally has lighting down to a better sort of solution where you can kind of do it a little more real time and it actually looks good and everything, right? And so it's been a very, very long, hard road for 3D graphics to get to that point as well. And if you were to see the stuff that we would be doing, if this were 3D Handmade Hero to do lighting, you would be very, very unhappy, I promise you that, because there's just a ton of stuff involved there. Not to mention we'd have to be in HDR, which is a whole other issue. Is your lighting cube idea the same thing as cube maps? So I'm sorry if I didn't say, I thought I said cube maps here. I was describing cube maps. That's what I was describing here when I was saying this is how sometimes people do it in 3D. They call them light probes, and they're typically cube maps or something similar rendered at various locations throughout the world that they then interpolate between. And that's just one example of one scheme. There are many schemes that one might employ to do sort of the indirect lighting part of the indirect lighting equation. Because really that's what this is all about, right? There's the direct term and the indirect term, right? And this one's the easy one. The direct part of the lighting is just the part where the light bounced off the surface directly and into your eye, right? That's really simple. So and when I say light, I don't mean the generic light. I mean like the light source, like the sun. The direct path that the sun took off that surface directly to your eye. The indirect part, which is all the other stuff coming from everywhere else, where the sun bounced off something and hit it or whatever, right? That's the hard part because it's coming from every direction. This is one direction, like the band. I'm sure they're a fantastic rock group or whatever it is that they do. And this is many directions, and many directions is much more difficult. They don't sell hardly as many albums. How to feather light through a window or tree. So I guess so you're trying to clarify the question I was looking for. That doesn't really clarify it, unfortunately, but I'll answer the question about as if it's about translucence, hoping this will help you, because I'm not sure what you're asking. But here's translucence. So let's suppose I take the classic example of translucence, and we'll say inside Japan and outside Japan. So the classic example in Japan would be a shoji screen, right? You ever seen these things? They're like, they're kind of cool. They got like a lattice of wood, right? And then inside the lattice of wood, there's like this sort of paper, sort of paper. And they're very characteristic because what happens is they just kind of light up when there's light on the other side, like the sun on this side. They just kind of are a nice pleasant gray. And if someone was standing here really close to them, you would see their shadow projected onto it, right? But you'll never see them. So it's not transparent, right? It is not a transparent surface. It is a translucent surface. And if you're anywhere besides Japan, then that's where the tree comes in. So if you're to look through a leaf, right, one of the leaves of a tree at the sun, right, you kind of see this brightness there. And if there was another leaf that was obscuring it, you'd see the shadow on there, right? So you kind of see the presence of light on the other side, but you don't see the actual objects at all, right? And that's translucence. I assume that's what you're talking about. I'm not sure. The reason is because you said feather light through a window, but a window is transparent. Really all a window does is have an index of refraction, which bends light, but it doesn't tend to really absorb it or rescatter it in that way. But so I'm going to just answer the question for translucence. And so the answer here is translucence is really actually pretty straightforward. It's another aspect of the indirect light transport. So remember how I said, okay, I'm viewing the surface, right? And here's the light, okay, right? So if I wanted to start to, and I've got my indirect light coming in from here, right, bouncing off. If I want to start handling translucent surfaces, they are typically thin. What you end up doing is you just have an infinitely thin, your polygon or whatever it is, right? And you have the light that comes from the back. So if the sun's back here, and there's indirect light coming from all of these angles, what you start doing is you actually look at the light that comes in here and you scatter that light through the other side, right? So basically all translucence is indirect lighting equations that are operating off the back of an object instead of just the front, right? Hopefully that helps. Why don't we just have the lighting feigned on the sprites? The reason is because we don't know ahead of time where the light is coming from. So if we want the light to be able to circle around the tree and the tree to light up differently depending on where it is, There's no way we can bake that into the sprite. We need to be able to compute it dynamically. So the lighting that we can bake into the sprite is the kind that you see here, where, which is what we'll do, which is like sort of a general lighting and self-shadowing of the light of the tree on itself. But in terms of light that moves around the object, in order to portray that, we have to be able to compute it dynamically. How about the second frame buffer you mentioned with light sources having pre-computed distance falloff plus graphics objects having another channel similar to alpha that indicates reflectivity? That would be fast and maybe good enough for a 2D game. Yeah, and so that's sort of what I was getting at when I was saying, we blurring it out there was like, that's the distance falloff. So the problem, and this is, again, this is why lighting is so hard. This is why lighting is even more difficult than, say, fluid dynamics, or other volumetric things. It's because lighting, at least in 2D, lighting doesn't care how far the light travels, really. So the problem is that, again, and this is something I didn't mention because this is not supposed to be a complete course on lighting, so I gave you the very, very simple overview of everything. It gets a lot more complex if you go all the way down the rabbit hole. But basically, like, one thing you might say is illumination is constant along a line. And this is the big thing about lighting. Basically, when light starts traveling in a line, it just goes in that line forever. And if it doesn't hit anything, it will be just as bright when it hits the end as it was when it started, right? And so really the only thing that's making light get dimmer ever is when it hits something. Now, unfortunately for us, air just isn't that thick. So when you have something like in our game where we have a light source over here and something all the way over here, let's say that was highly reflective, like a mirror ball, right? Well, this light should be super bright in this mirror ball. And it's all the way on the other side. There's no fall off. Like, lights don't have a fall off. That's really not a thing. The fall off of light at the scale that we're talking about is literally non-existent. It does not happen unless there's some real thick fog in here or something, right? And so fall off really isn't quite right. Now, what we may do, again, like I said, because we don't have the luxury of it, is we may just end up using a fall off because we have to, right? And that might be what we do, because again, with games, you have to compute in real time. You just don't have the ability to just say, well, we're going to just simulate everything accurately. That's not an option. So we'll see what our approximation ends up being, but it's always worth noting that things like fall off don't even really happen with lights. And so that's a bit rough. But what we could do is maybe like, again, maybe we use point lighting to get that. And then our diffuse lighting, well, maybe we don't care because you wouldn't see the diffuse lighting travel that far, right? And so the fall off can happen there or something, right? Due to the complexity of lighting, are system resources a major factor consideration in shading engines? Sure. I mean, if you go look at when you, can tweak a game settings, oftentimes like shadow detail and things like this are things that get set in the game settings. So, it's definitely the case that the beefier the GPU in a machine, the more lighting you could do on it, right? If that's what you're asking. I'm not totally sure that I know what you're asking, though. If you use a 2D lighting buffer, will you need to generate a G buffer or Z buffer as well first? Well, probably not a Z buffer, but we're going to need something to control the propagation here. So a G buffer is probably sort of something like what we might use, in the sense that We want to be able to knock out, to prevent light from traveling in the direction where there are solid objects. We want to, reduce the amount of light. So we'll see how we do that. I'm not sure how we'll do it. What about bleeding effects? I do not know what that means. Is this going to work with software rendering, or will it be too computationally expensive? Well, we'll implement it in software rendering, and if it turns out that we can't get it to run fast enough, we'll just turn it off in the software renderer. But yeah, if it's too slow and we can't optimize it enough, then we'll only run it on the GPU path. But we'll at least make it work correctly in the software path so that we can see how to do it. And then if we have to rely on GPU horsepower to actually render it at real time for the gameplay, that's fine. You mentioned computing values for a single source receiving light from multiple sources. How would we, in essence, do this computation? I'm assuming this is based off neighboring pixel values. I'm having a hard time formulating an approach. So again, the approach is kind of the same as I was talking about up here. What I'm thinking is basically, we compute something which we then subsample down. So we have our 256 by 128, and we sample that down to a 128 by 64, and a 64 by 32, and a 32 by 16, and a 16 by 8, and an 8 by 4, and a 4 by 2, and a 2 by 1, and a 1 by 1, right? And then when we want to get blurrier and blurrier versions of the light that's coming from an area, we would just sample those, right? So yeah, so I don't know what we're going to do exactly. We will play around with it, and again, like I said, one of the things I like to do on the stream is I like to tackle some problems on the stream that I've never tackled before, because one of the things I like to show on the stream is how to tackle problems. And if all I ever do is show you stuff that I already know how to do, well, that doesn't really show you how to tackle new problems, right? So, so we'll play around with it and we'll see where we get. Wouldn't it, in most cases, be smarter to use an existing graphic render engine and just focus on coding the game itself gameplay? Asking a question in the abstract like that presupposes that you already had a specific goal in mind, and that goal was to make some gameplay, right? And so if your entire goal is that you wanted to make some gameplay, then yes, it would probably be a much smarter idea not to spend your time coding graphics. However, I don't think it is a good idea to assume that what makes a game or what makes a game developer is just the fact that someone sat down and was only thinking about gameplay, right? Game development is an entire discipline. It is not about you had some specific idea for gameplay and the only thing that you wanted to do was implement some gameplay, right? That's sort of like saying, why would you paint a picture of a flower when you could take a photograph of the flower, right? And it's like, well, that presupposes that your goal was to reproduce a flower as accurately as possible, a particular flower somewhere, right? And so what I would like to emphasize is that game development is a thing that you do. It is like any other artistic endeavor. There are many aspects to it, and where you find enjoyment may not be the same as someone else. And presupposing a singular purpose, that is, I just want to get gameplay as quickly as possible onto the screen, supposes that you had a very specific goal in mind. And I, for one, never have that particular goal in mind, and I suspect there are many other people who don't either. And those are the people who just enjoy developing games in general, right? They enjoy the process of making the parts of a game, which may have nothing to do with the gameplay at the end of the day, right? And to emphasize how important this is to everyone, that there are people like this, the only reason you even have the option of using an existing renderer or some other technology or engine is because there were people who didn't just sit around thinking, well, I just want to make some gameplay, right? And so it takes all sort of aspects of the discipline to move the discipline forward. And it's very important that there are people out there who enjoy working on all the different pieces. And so, like I said, this stream is for the people who want to know how to build the whole game, not people who just want to put some gameplay on the screen, because you can just go download Game Maker if that's all you wanted to do, right? What is the ambient occlusion, and why my video card get late to run games with ambient occlusion, like really lose FPS? So I can't speak to specifically why a particular game might be running more slowly with ambient occlusion or anything like that, but I could give you some hypothetical answers. I can tell you what it is. So ambient occlusion we didn't have to talk about, thankfully. And the reason for that is because it's baked into the sprites actually fairly well. But let's talk about what it means. So ambient occlusion is a term that actually, it's not real, right? It's not a real thing, okay? All the stuff I talked about up there before were real things. Ambient occlusion is a term that actually refers to an effect of real things, not some aspect of what's actually happening to the light. And what it's referring to is the fact that if you take a look at a surface, okay, let's say I have a surface that looks like this. Well, my light source is able to hit all of the pieces of this surface. So when I am rendering it, I do not have to consider the fact that there is light getting absorbed by this surface when I light this surface, and vice versa. A and B are completely unrelated, okay? However, if I were to consider the same light source now operating on a different surface, right? Let's suppose the surface looked like this, okay? As the light kind of comes in here, what you can see is that a certain degree of the light that should have been falling on this surface is not going to fall on it because other surfaces in the area were preventing that from happening, right? So if the light comes from over here, yes, I can hit it, but if the light comes from over here, I can't. Furthermore, if it looked more like this, then I've got even more of that happening, right? Light from anywhere here is going to shadow this interior part, light from in here is going to shadow it, and so on. So ambient occlusion refers to the process, and again, so ambient meaning light from all directions, not a specific direction, and occlusion meaning to block, right? Ambient occlusion is a fake and actually kind of lousy approximation to recapturing some of the detail that is lost because you're not actually doing lighting calculations at the fidelity necessary to capture these effects. So what happens is you take a surface like this, you take a look at this here, and you say, well, I'm gonna, before I ever run the game, before I do anything, I'm gonna look and see how much of the horizon it can see, right? And more specifically for a particular texel. So like right there, you know, like right that point. I'm gonna cast out the horizon, I'm gonna see that, okay, it can see about that much, right? So when I am lighting things, just in general, when I'm using the indirect lighting term, so light coming from everywhere, if it can only see 25% of the horizon, I'm just going to multiply the incoming light by 25% and call that the darkening effect, right? Call that ambient occlusion. And so what ends up happening is in places where objects have crenellations or folds, you know, in-skews things, it darkens them. So that's ambient occlusion, and there's two types that are typically used. There's baked, and there's screen space. So there's baked ambient occlusion, screen space ambient occlusion. Baked ambient occlusion is when you do exactly this process offline. So I take my object, whatever it is, I go through it, and I have a texture map that covers its surface, and at every texel on that texture map, I see how much of the horizon it can see. When I say horizon, I don't mean that. I really mean hemisphere, right? The hemisphere around it. And I bake that into a term that's the ambient occlusion term. Now it can get fancier because there are ways oftentimes using things called spherical harmonics, which we're not going to talk about, or other kinds of bases, there are ways of trying to encode not just how much of the hemisphere is seen, but actually what sort of general region of the hemisphere you saw. And that allows you to do more directional ambient occlusion, right? But anyway, Baked.io computes that everywhere on the model and writes it into a texture map. So this comes out as a texture map per model, right? Or, textures that cover the model that say how much you can see, and off you go. Screen space ambient occlusion is a totally different idea. What screen space ambient occlusion is, and these tend to look real bad, but some engines do it better than others. But what this is this goes ahead and says, all right, look, we know we've already got a Z buffer, right? We already rendered a Z buffer into the scene, so we actually already know when we draw this thing, right? We actually already know the depth value at every pixel. So if there was a place in the scene that had like an in-skews part like that, and we wanted to darken it in there because of that, what we could do is at every point on the screen, we could look at the depth values in screen space that are nearby it and decide based on those depth values whether we think there were things that would be shadowing it that are nearby. And based on the collection of those depth samples, we will then darken the incoming lighting for that point. Okay, so that's screen space ambient occlusion. Again, these are not real things. These are hacks that are designed to increase the degree to which you capture in-skews lighting on things, because typical game lighting can't doesn't do full computations there, right? Like, remember I said there's that cube map lighting trick? So if you imagine something like that happening on an object, well, it's not ever casting any rays out. It's not ever seeing if it can actually reach that cube map. It's just assuming that it can. And so you never get that self-shadowing. That's what the ambient occlusion term's trying to put back in. But it's not a real thing. It's just a technique. It's like a hack to try and reproduce what would actually be happening if you were computing the lighting equation at every point for the whole light field. And T. Songberg cake. I do not prefer muffins. Do you have any plans to implement sprite opacity? We already do implement sprite opacity. Your sprites can be as translucent as they want to be. And if so, could this be taken into consideration with the light map calculations, i.e. less opaque objects block less light? Yeah, and we could even try to make translucent objects, or transparent but colored objects, transmit that light color. I don't know. We'll see what we can do. We'll just give it a shot. That's one of the fun things about writing your own graphics engine. We could come up with some techniques that no one's ever done before, and maybe they look good, or maybe they look awful, but it's a lot of fun to play around with, and so that's one of the things we'll do. Maybe that's what we'll spend next week doing, just playing around and see where we get. Are there any books or resources you would recommend on lighting? So, I guess I've never read it myself, but there is a book on lighting that a lot of people recommend. Let me see. It's by, I think it's by Matt Farr. Yeah, this is the one. This book. Yeah, I feel like this is a book that a lot of people respect. I have not read it myself. So, don't hate me if it turns out to be awful or something, but I believe if you want to know the math behind how light actually works and how to simulate it, I feel like that's one of the books that people recommend for a good, a good kind of full overview. Twister. So game design documentation like a roadmap for the game. No. So we are not doing anything like that. This is a game implementation stream, so the design is kind of a separate thing that we don't really work with. We just do programming the engine, and then the gameplay as well. We'll be programming it, but we're not actually talking about that part. Because I'm not really a game designer, so I don't want to try to give lessons on how to do game design because I'm the wrong guy for that. So yeah, so we're not dealing with any of that stuff in terms of design docs or anything like that. Wouldn't a game in pitch darkness have the easiest lighting system to code? Yes, it would. And there almost was a game that was done in complete pitch darkness. You may have heard of it. It was called Alone in the Dark. And my understanding was it was supposed to be entirely audio only, but the publisher eventually made them change it, and so then they ended up doing it as a bitmap with 2D objects over it game. This was the original Alone in the Dark, not the remake, obviously. But it was very successful anyway, but my understanding was that it was originally supposed to literally be a black screen, and the game was played entirely in audio. But they made them change that, so it didn't happen. But that would have had very easy lighting. Can you go back in time and start this series 15 years ago? I would love to be able to go back in time 15 years. You don't know how much I would love to do that. If you can provide me with some sort of a device that would allow me to do so, I would happily start the series 15 years ago. Of course, we wouldn't have Twitch and YouTube and stuff, so we'd have to figure out a way that we were going to transmit it, but I'm sure we could figure it out. And T Songbird, it is neither cheese nor mud cake. I like the sort of cake with buttercream frosting. Okay, so we're still trying to chase down this question. What I mean is sort of more like how to make beams of light pass through a rendered object. Okay, so, and Garlando Bloom tries to clarify, I think they meant God rays. Okay. So God rays is actually volumetric scattering. Okay. So the way that this works is there's no such thing as beams of light, right? They're just photons flying through the air. And what's actually happening, when the reason this occurs is when the air around something is highly particulate, right? So it's typically bright light. So there's a lot of photons, right? Lots of photons. And heavy air, right? Lots of particles, right? So you're typically talking about sunlight, bright sunlight, misty air, that sort of thing, or dusty. That's when you get into these heavy volumetric scattering situations. And what's happening there is you end up with stuff like, okay, I've got a window, right? And it has, it's got, it's got Jesus in it, right? And a vampire or whatever. And Jesus is like about to kill the vampire with a stake or something, right? I don't know. It's a stained glass window is my point. I don't know if the vampire, maybe it's got some bat wings or something on there. So there's a stained glass window, right? And the light's on the other side of it, and it's coming through. And what you're asking about is like, well, they're these colored light rays that like pass through, right? Or something like this. And the way that happens is the light, when it hits the stained glass window, the stained glass, the whole point of stained glass is it absorbs certain colors and lets others pass through. So if you see red stained glass, like, Jesus's vampire killing stake is like dripping some blood or whatever, so that's red, right? What that means is it absorbs stuff outside of that wavelength. So basically, like, here's red on the wavelength spectrum, here's like a bunch of other things. It's absorbing all of this light into the glass, and it's letting this pass through. So the light on this side may be whatever color, but when it comes through here, it's going to be red. What then happens is all of these photons that are streaming through here that are red, they hit all that particle matter in the air, all the dust that's in the spooky church or whatever, right? And it hits that and scatters in all directions. Some of those directions come back to your eye. And so that's what's actually happening. It's a volumetric scattering problem. And so, if the question is how do I implement that in a ray tracer, well, the answer is you literally do the volumetric scattering. What you do is when you cast rays, right, you have volumes and they are defined as having a certain density of volumetric particles in them. And as the ray passes through them, you compute a percentage chance of it getting scattered, and then you, if it hits, you scatter that ray, and you sample that proportional to what you believe the incoming light field is in an unbiased way, and all this other nonsense, right? If you're trying to figure out how to do that in a game, then you're in hack territory, right? Because volumetric scattering is one of those things that you got to do an approximation to of some kind. And so I have to say, I don't know what the current, I don't know what the current slickest technique is for that. I don't know. For God rays, I suspect that it would have something to do with taking one of these guys and going, well, okay, we're going to presuppose that we know what our surfaces are that do God ray pass through stuff, and we're going to go ahead and oh, well, you know what I just thought of? They might just do it in screen space now that I think about it. Yeah, okay, so there's probably a screen space way to do this now, actually, because we've got so much ability to do that. I wonder, what they might do is just take a look, they might just take a look at render places that want to have volumetric effects in them. They might just use screen space for that. I don't know, you should look this up. I wonder if there's some stuff, because this is what I was thinking. I wonder if there's screen space God ray techniques now. It seems like that's the way you do it, and you would kind of go through the screen. You would see if you had God ray pixels. If you did, you would sort of set them, you would do maybe perhaps the raycast just right there, or you'd do a cube map lookup right there. That might be. So it might actually be that you do this in screen space nowadays. I don't know. I'd be curious to know. I've never implemented God rays at all, really. I've never tried to implement God rays, so I don't know. But that's what's actually happening. I suspect that nowadays maybe screen space is how they would do that, because it seems like that's probably the only way to really handle it without doing anything crazy. Don't you cast rays from the eye and not the sun to reduce calculations, and then see if the rays cast from the eye hit the sun? So I'm not sure what you're actually referring to, because again, in games we don't really do a whole lot of ray tracing. I mean, sometimes we do for computing things nowadays, but you don't really cast rays from light sources or from eyes, if that makes sense. You do render shadow maps from light sources, so in that sense you are casting rays from the sun, if you will. So yeah, you don't do it that way. But if you're making a ray tracer, the answer is typically that you do go from the eye out in purely Monte Carlo ray tracers. I shouldn't say purely Monte Carlo. In forward Monte Carlo ray tracers, which are fairly common, you go from the eye outwards. But in a whole suite of other ones, you actually go from both. They're called bidirectional path tracers. So Metropolis ones, they go from both. Bidirectional path tracers go from both. So no, I mean, the answer is you don't exclusively go from one or the other. It really depends on what you're implementing, which one you go from for what. Can you use a 3D overlay to pretend, say, a slice of a 3D environment? For example, the platform you're on being Z, and then X is across, Y up and down, so you can have a light source at X33, Y50, Z1, so all objects less than X33 would be shadowed to the right, objects greater than would be shadowed to the left. That is sort of what I was talking about, but again, I don't know how crazy we'll get with it in terms of 3D-ness. Yeah, I'm not sure exactly what we're talking about, but again, let's wait till we get a little bit more into trying to play with that stuff before we talk about it more, because we're not sure exactly what we're going to try. In early episodes, you worked on having multiple Z levels. Wouldn't this mean you would need to render walls in 3D, thus introducing some 3D into the rendering and lighting calculations? Possibly, but I think I'll probably try to handle that again in slices. Like, I don't know that we want to try and do full 3D for that. I think we might want to just have like lighting on 2 different planes or whatever, right? Or maybe just one plane, whatever the plane you're on has lighting and the other ones don't. Stuff like that. How often do you stream game development? Every night at 5 p.m. Well, except weekends. My lord, there's a lot of questions. I think I might have to end the Q&A soon. My voice is getting tired, and I want to have dinner. What is your background that led to where you are? Is education or important or interest more important? We've covered that on earlier episodes. I'd probably recommend going back and watching earlier episodes for more exposition on that. Will this lighting system work for blind people? So the important thing for blind people, right, is it's very much like deaf people. You want to just do it really loud, right? So if you want the lighting system to work well for blind people, you need to increase the brightness to a very high level so they can see it, obviously. I mean, right, that goes without saying. I'm telling you stuff you already know, but... Do you think we'll be able to do all this in real time, or will we have to pre-bake some of the lighting information when generating the map? Don't know. I really don't. It's all conjecture at this point. Couldn't you just make a 3D game and then flatten it with a rolling pin? That's not a bad idea. I do agree that would be an easy way to create 2D assets out of 3D assets, but I'm afraid they might smush out too much. So that you have to figure out how to solve that problem. How often is real-time radiosity used in games? Is it easy, and do you guys use it? Why or why not? Well, so real-time radiosity, I wouldn't use the term radiosity because radiosity is a specific technique, right? Radiosity is really not, you know, without going into too much detail, radiosity is a scheme that's about solving for the heat transfer in lighting space between surfaces, right? And it's not really that common in games. I think maybe Frostbite uses a licensed radiosity transfer engine, maybe. But a lot of people just aren't using any of that stuff anymore. They do real-time lighting, but it's not radiosity. It's done in different ways. And so radiosity is a technique, not an effect, right? And so I would say that real-time lighting that does include indirect lighting is now much more commonplace. Like I said, Unreal 4 has a lot of it in there, I believe. They have like, I think they have sparse voxel octree stuff in there now for lighting, where they actually do like, you know, real-time diffusion. Crytek has, you know, a voxel light propagation scheme. So it's in many professional 3D engines now, but it's not necessarily radiosity. Radiosity is a very specific type of a technique. GGMTV, I saw a game that uses normal maps on sprites. There are many games, I want to say, there are many games that use normal maps on sprites. It's still not actually that common. Like a lot of sprite games don't use normal maps. But it's definitely not super rare. Like there are plenty of games that have shipped with normal maps for sprites. The question is usually just how do you generate them, right? If you render your art assets from 3D down to 2D, it's trivial. But if they're hand painted like ours are, it's a question of who makes them and how, right? Isn't light's fall off inverse square? As you move farther from the light source, each ray is further from its neighbors. So no, there's two separate things, right? And this is kind of crucial. Again, this is not a complete lighting course, so you know, I don't go into detail about everything. But the inverse square law is actually only affects part of your light. So let me give you a little. I'll try to explain a little bit how that works. So basically, remember I said there's the indirect and the direct light, right? And so if you think about how the light works, if I have incoming light and outgoing light, like so, then the inverse square law really does not affect a single photon path coming from a light source and bouncing off, right? And so if I'm trying to figure out how bright a reflected light source is in a mirror, there is no inverse square law calculation. The only thing that the inverse square law affects is how big the light appears to be in the mirror. Does that make sense? So basically, the inverse square law, if I had a mirrored sphere, the only thing the inverse square law says is as the light gets further away, it will be bigger or smaller. Like if it gets further away, like here's if it's close, right? And here's how big it would be if it was far. So the inverse square law, that's what happens there, right? And that's because, again, the light, obviously, like you were saying, if I have a constant density of things that are showing out, along this, whatever the solid angle is, right? Then the further away I get, the more spread out those photons are going to be, right? But for a given one, it doesn't matter. So the size of the light source projected onto the object does fall off with inverse square law, but its brightness does not, okay? So what that means is that, yes, you will have a inverse square law effect in terms of how much light in total may reach an object based on how far away the light source is, because the bouncing around from different angles will get more sparse as you get further away. But for the pure reflected part, it's actually just the size of the reflection that changes, but the brightness is intact. And I know that's a little counterintuitive, but that's just the truth. And so there is no inverse square law for brightness. It's not really a thing. I should say for the pure reflective part. That's more for the diffuse bouncing around part, if anything, right? Would you consider voxelizing the scene like Little Big Planet 2 does? Yeah, so, honestly, that's what I was sort of talking about here, right? Literally, that is sort of what I was thinking in my head, was that kind of a scheme, right? You put in the light sources, you diffuse them, and then you have, like, you know where your objects are, so you kind of remove the light from there, like a voxel kind of scheme, right? Only we're 2D because we don't, so we don't have voxels per se. And so, yeah, like to a large extent, that is exactly the sort of thing, like Little Big Planet style lighting is exactly the sort of thing I was thinking of. Let's just see if there's any more good questions here. There's just so many questions. I'm not going to get to them all. So I'm just going to see if there's any other ones that I really think we should answer. Had to log in, so hopefully this isn't too late. Wouldn't there be fall off with a point source when integrating across the surface since the rays spread out away from the source? Okay, so I think we just covered that. And so the answer is that is for ambient lighting terms. That's for the indirect lighting terms we'll do that, but not the direct lighting terms. And it's a common misconception too about that, right? Like how that works exactly is the inverse square law doesn't affect light along a line. Light is constant along a line. So only once you start talking about areas do you care about that. So it depends on which part of the reflectance you're trying to compute, whether or not the inverse square law affects the size of it or the brightness of it, right? And so, yeah, you can't just say that light falls off with inverse square law because that's not actually true. The brightness of light is constant along a ray. It's about what the actual effect is that's happening on the other side, whether the spread of those rays end up causing a diminishing brightness effect, which is the case for purely scattered light, or a smaller size effect, which is the case with pure reflectance. Why is it easier to represent light as photons and not particles in 3D programs? I don't think it is. Like, you're not... First of all, photons are kind of particles, right? I'm sorry, I don't think I understand the question. I guess I'll say about that one. Rendering light in environments and events approaching the speed of light. How to do it? I don't know. Good luck to you. I'm sure that's a whole relative... That sounds like something Mark ten Bosch would do. PBR lightning. I don't know what PBR lightning is. Quick rundown on how it works. I'm afraid I cannot give you a rundown on how it works because I don't even know what PBR lightning is. You mean like lightning from the sky lightning? I'm not sure. All right, I think we've come to the end. We have come to the end, but I understand that John is streaming now. Some people are saying that John's streaming, so if you want to watch some more stuff right now, you should go check out his stream, Naysayer88 on Twitch. I may well be going to check out his stream as well. So yeah. All right, let's go ahead and wrap this up. Tomorrow we will start working probably with normal maps. That'll be the first part of the stuff that we do. So I hope to see you back here tomorrow, 5 p.m., right here, same time, same place on Twitch. It's been a crazy Q&A day. I don't know what happened there. Maybe we were on the Twitch front page again or something like that. But glad to see new people asking questions. And there were a lot of good questions too, which is pretty awesome. Again, thank you for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. I will hopefully see you guys again tomorrow or on John's stream after this. In the meantime, if you would like to pre-order the game to get the source code, you can do that on handmadehero.org, and it comes with the source so you can play around with the techniques that we're talking about here on the stream and see how they work. You can also subscribe to our Patreon if you want to support the video series. It's always much appreciated. We also have forums where you can ask questions, and there's also ports to Mac and Linux and stuff like that on their community, contributed stuff and annotated episode guides. It's all good stuff, so I highly recommend checking that out. And if you want to be able to catch the stream live, we have a tweet bot you can subscribe to that tweets the schedule at you. So I highly recommend checking that out if you're trying to catch us live. It's the best way to stay up to date. So thanks everyone for joining us, and I will see you hopefully tomorrow. Take it easy, everyone.